In the scorching heat of the Gobi Desert, where temperatures routinely soar past 110 degrees Fahrenheit, a discovery was about to change our understanding of prehistoric life forever. It was August 23, 2023, when Dr. Sarah Chen's trained eye caught an unusual glimmer among the russet-colored sedimentary rocks. That moment would mark the beginning of what scientists now consider one of the most significant paleontological finds of the 21st century. The bones that emerged from the ancient soil would tell a story that had remained hidden for 66 million years, challenging everything we thought we knew about the apex predators of the late Cretaceous period. As the excavation team carefully removed layer after layer of sediment, they uncovered what appeared to be the most complete theropod skeleton ever discovered in the region. But this was no ordinary dinosaur. The creature's unique anatomical features immediately set it apart from any known species, suggesting the existence of an entirely new lineage of predatory dinosaurs that had somehow escaped scientific detection until now. The skull alone measured 1.8 meters in length, rivaling that of Tyrannosaurus rex, yet its structure displayed characteristics never before seen in any theropod fossil. The initial analysis revealed a fascinating paradox. While the creature clearly belonged to the theropod family, its skeletal structure exhibited adaptations that seemed impossible for its time period. How could such an advanced predator have evolved so early? And why had no trace of its existence been found before? These questions would soon spark one of the most heated debates in modern paleontology. The site itself presented another mystery. The sedimentary layers surrounding the fossil suggested an environment vastly different from today's arid desert. Evidence pointed to a lush, subtropical forest ecosystem that once thrived in this now desolate region. The preservation quality of the specimen was exceptional, with even some soft tissue impressions visible in the rock matrix, a rare occurrence that would provide unprecedented insights into the creature's biology. As word of the discovery spread through the scientific community, researchers from around the world began converging on the remote dig site. The implications of this find were too significant to ignore. Here was a creature that seemed to possess hunting adaptations more sophisticated than those of any known theropod, including the mighty Tyrannosaurus rex. Its forelimbs, unlike the famously reduced arms of T-Rex, were proportionally longer and showed evidence of highly developed musculature. What kind of predator was this, and how had it remained hidden from science for so long? The mystery deepened as more of the skeleton was exposed. The creature's vertebral structure suggested capabilities for movement that would have made it an extraordinarily agile hunter, despite its massive size. Initial measurements indicated a body length of approximately 11 meters, making it one of the largest theropods ever discovered. Yet its bone density and distribution pointed to a level of agility that seemed impossible for an animal of such proportions. What forces of evolution had shaped this remarkable creature? How had it fit into the complex ecosystem of the late Cretaceous period? And perhaps most intriguingly, what role might it have played in the dramatic events leading up to the mass extinction that would eventually claim the lives of all non-avian dinosaurs? These questions would launch a new chapter in paleontological research, challenging long-held assumptions about dinosaur evolution and forcing scientists to reconsider the diversity of predatory strategies that existed during the age of dinosaurs. The implications of this discovery extended far beyond the field of paleontology. Here was evidence that the story of dinosaur evolution was far more complex than previously imagined. What other extraordinary creatures might still lie hidden beneath the Earth's surface waiting to be discovered? And what might this particular find tell us about the true diversity of life during the Mesozoic era? As the sun set over the Gobi Desert that evening, casting long shadows across the excavation site, the team knew they stood at the threshold of a new era in paleontological research. The mystery of this forgotten predator was just beginning to unfold, and its story would reshape our understanding of prehistoric life in ways no one could have predicted. The detailed analysis of the excavation site revealed a world drastically different from the barren landscape of today's Gobi Desert. 66 million years ago, this region teemed with life, supporting an ecosystem of extraordinary complexity and diversity. The sedimentary analysis revealed evidence of meandering rivers, dense vegetation, and a climate that more closely resembled modern-day tropical rainforests than an arid desert. The atmospheric oxygen levels were significantly higher, approximately 35% compared to today's 21%, creating conditions that could support massive creatures and complex food webs. Within this ancient environment, The newly discovered predator, temporarily named Enigmatherium gobiensis, would have ruled as an apex predator unlike any previously known to science. The creature's skeleton revealed adaptations that pushed the boundaries of what scientists thought possible for theropod dinosaurs. Its skull, measuring 1.8 meters in length, housed a brain cavity approximately 40% larger than what would be expected for a theropod of its size, suggesting cognitive capabilities that might have surpassed those of its contemporaries. The most striking features were its forelimbs, proportionally longer than those of any known large theropod, equipped with 3 fingers ending in massive curved claws, measuring up to 40 centimeters in length. The bone structure and muscle attachment points indicated a degree of dexterity previously unseen in large predatory dinosaurs. This combination of enhanced brain size and advanced forelimb development raised intriguing questions about the creature's hunting strategies and potential problem-solving abilities. Microscopic analysis of the preserved bone tissue revealed growth patterns that indicated these creatures reached maturity faster than other large theropods, potentially giving them an evolutionary advantage. The bone structure showed evidence of an advanced air sac system, suggesting a level of respiratory efficiency that would have allowed for sustained periods of high-energy activity. This respiratory system, coupled with powerful leg muscles evidenced by pronounced muscle attachment points, painted a picture of a predator capable of both explosive speed and endurance hunting. The discovery of multiple specimens in close proximity suggested these animals might have exhibited social behaviors, challenging the traditional view of large theropods as primarily solitary hunters. Trace fossils found in the surrounding area, including footprints and feeding sites, provided tantalizing glimpses into their daily lives and hunting strategies. The spacing and orientation of these traces indicated coordinated movement patterns, raising the possibility of pack hunting behaviors more sophisticated than anything previously documented in the fossil record. Environmental data gleaned from the surrounding rock layers revealed that Enigmatherium gobiensis lived in an ecosystem experiencing significant climate fluctuations. This suggested a remarkable ability to adapt to changing conditions, perhaps explaining its advanced features as evolutionary responses to environmental pressures. The diversity of prey species found in the same geological formation indicated a predator capable of taking down everything from medium-sized herbivores to the largest sauropods of the period. What selective pressures had driven the evolution of such an advanced predator? How had it coexisted with other large theropods known from the same time period? The answers to these questions would require a fundamental reassessment of late Cretaceous ecology and the evolutionary dynamics that shaped predatory dinosaurs. The presence of Enigmatherium gobiensis suggested that the final chapter of dinosaur evolution was far more complex and diverse than previously imagined. The analysis of dental wear patterns and bone microstructure revealed a creature with a bite force estimated at more than 6,000 kilograms per square centimeter, comparable to that of Tyrannosaurus rex. However, the unique jaw morphology and tooth serration patterns suggested a different hunting strategy, possibly involving more precise killing techniques rather than the crushing bite typically associated with large theropods. This combination of advanced features, larger brain, sophisticated forelimbs, powerful bite, and potential social behavior, painted a picture of a predator that might have represented the pinnacle of theropod evolution before the mass extinction event that would claim the lives of all non-avian dinosaurs. What other evolutionary innovations might have emerged had the asteroid impact not brought the age of dinosaurs to an abrupt end? The implications of these findings extended beyond paleontology, offering insights into the potential for convergent evolution and the development of intelligence in predatory species. How close had these creatures come to developing even more advanced capabilities? What might they tell us about the evolution of intelligence and social behavior in predatory animals? The announcement of Enigmatherium gobiensis at the International Paleontological Congress in Berlin sparked immediate controversy within the scientific community. Dr. Marcus Rodriguez, a leading expert in theropod evolution from Oxford University, challenged the validity of the find, arguing that the combination of features described in the specimen defied known evolutionary patterns. His critique centered on the statistical improbability of finding a completely unknown large theropod species, so well preserved, yet previously undiscovered in a relatively well-studied region of the Gobi Desert. The debate intensified when Dr. Yuki Tanaka, from the Tokyo Institute of Paleontology, presented detailed CT scans of the skull, revealing neural pathways and brain structure implications that suggested cognitive capabilities far beyond what was previously thought possible for late Cretaceous theropods. The scans indicated enlarged areas associated with social behavior, spatial reasoning, and problem-solving, leading to heated discussions about the potential intelligence of these creatures. Could a predatory dinosaur have evolved such advanced neural architecture 66 million years ago? Further controversy erupted over the dating of the specimens. Initial radiometric analysis placed the fossils at exactly 66 million years old, meaning these creatures would have been among the last dinosaurs to exist before the Cretaceous-Paleogene extinction event. However, their advanced features suggested an evolutionary timeline that should have required millions more years of development. This temporal paradox led some scientists to question either the dating methods or the interpretation of the anatomical features. The scientific community split into three main camps: those who accepted the findings as presented, those who believed the specimens represented an already known species, with unusual preservation conditions creating the appearance of novel features, and those who suggested the fossils might be an elaborate hoax. The latter group, though small, pointed to the seemingly impossible combination of advanced features as evidence of fabrication, forcing the research team to submit their findings to unprecedented levels of scrutiny and peer review. A turning point came when independent analysis of the sedimentary layers confirmed not only the age of the fossils, but also revealed trace elements consistent with a major dietary shift among large predators in the region. This shift coincided with significant climate changes that would have placed enormous selective pressure on apex predators, potentially driving rapid evolutionary adaptations. The presence of similar trace elements in other fossil sites across Asia suggested these creatures might have been more widespread than initially thought, though their complete specimens had simply never been found before. The debate over Enigmatherium's hunting capabilities reached new heights when biomechanical engineers from the Massachusetts Institute of Technology created detailed computer models of the creature's musculature and skeletal structure. Their analysis revealed a predator capable of running speeds up to 50 kilometers per hour, while maintaining the agility to make sharp turns, a combination previously thought impossible for an animal of its size. The models also suggested that its enlarged forelimbs could have generated enough force to literally throw smaller prey animals, a hunting technique never before documented in theropod dinosaurs. Questions about social behavior became even more complex when satellite imaging and ground-penetrating radar revealed additional burial sites containing multiple Enigmatherium specimens in various growth stages. The spatial distribution and positioning of these fossils strongly suggested these creatures lived and died in family groups, challenging long-held assumptions about predatory dinosaur behavior. This evidence of social complexity, combined with their enlarged brain capacity, raised provocative questions about the potential for primitive cultural behaviors among these dinosaurs. The most contentious aspect of the Enigmatherium discovery centered on its implications for dinosaur extinction theories. If such advanced predators had evolved by the very end of the Cretaceous period, what did this suggest about the trajectory of dinosaur evolution? Were these creatures on the verge of even greater evolutionary innovations when the asteroid impact occurred? The presence of such sophisticated predators so close to the extinction event forced paleontologists to reconsider their models of dinosaur evolutionary potential. Genetic analysis of preserved proteins, a breakthrough that many initially doubted was possible, revealed molecular evidence of advanced immune systems and complex hormonal regulation, suggesting these creatures possessed physiological adaptations more sophisticated than any previously known dinosaur species. This finding raised fundamental questions about the pace of evolution and the potential for rapid adaptation in response to environmental pressures. As the scientific community grappled with these revelations, new methodologies and technologies were developed specifically to study Enigmatherium, advancing the field of paleontology in unexpected ways. What other revolutionary discoveries might these new techniques reveal about the history of life on Earth? And how many other extraordinary creatures might still lie hidden in the rock layers beneath our feet, waiting to challenge our understanding of evolution once again? The reconstruction of Enigmatherium gobiensis's daily life emerged through a combination of cutting-edge technology and painstaking scientific detection work. Microscopic analysis of preserved skin impressions revealed a covering of proto-feathers, not for flight, but for temperature regulation and possibly display. These filaments, ranging from 15 to 30 centimeters in length, would have created an imposing silhouette, particularly when combined with the creature's 11-meter length and estimated weight of 7,000 kilograms. Trace fossils provided an unprecedented window into hunting behaviors that redefined our understanding of predator-prey dynamics in the late Cretaceous. One particularly well-preserved site in the Gobi Formation captured what appeared to be a coordinated hunt involving 3 adult enigmatheriums pursuing a herd of titanosaurs. The footprint patterns showed sophisticated flanking maneuvers, with 2 individuals herding the prey while a third moved to intercept, a level of tactical coordination previously thought impossible for theropod dinosaurs. The hunting capabilities of Enigmatherium reached far beyond simple pursuit predation. Analysis of their specialized forelimbs revealed they could exert a pulling force of over 2,000 kilograms, allowing them to literally drag down large prey. Their unique shoulder girdle structure permitted a range of motion exceeding that of any known theropod, enabling them to grapple with prey in ways that would have appeared almost mammalian. This combination of strength and dexterity would have made them formidable opponents even for the largest herbivores of their time. Dental microwear patterns told a story of diverse hunting strategies. Their teeth showed evidence of both slicing through flesh and crushing bone, suggesting they were capable of processing every part of their prey. Unlike many other large theropods, which often left significant portions of their kills unused, Enigmatherium appears to have been remarkably efficient in its feeding habits. This efficiency might explain their success in an ecosystem already populated by other large predators. The discovery of multiple preserved stomach contents revealed a surprisingly varied diet. Beyond the expected remains of large herbivorous dinosaurs, scientists found evidence of smaller prey, including primitive mammals and birds, suggesting these predators were capable of both power hunting and precision killing. This dietary flexibility would have given them a significant advantage during times of environmental stress, allowing them to survive when more specialized predators might have struggled. Perhaps most remarkably, analysis of brain endocasts suggested these creatures possessed neural architecture capable of processing complex social information. The enlarged cerebral hemispheres, particularly in regions associated with social behavior and problem-solving in modern animals, pointed to cognitive capabilities that might have included rudimentary tool use, a behavior previously thought impossible for non-avian dinosaurs. Evidence from multiple sites suggested they might have used objects in their environment to aid in hunting, such as driving prey against natural barriers or using terrain features for ambush attacks. The social structure of Enigmatherium groups appears to have been remarkably sophisticated. Age distribution patterns at various sites suggested they lived in stable family groups of 8 to 12 individuals, with evidence of cooperative breeding and extended parental care. This social complexity would have required significant cognitive capabilities, supporting the anatomical evidence of their enlarged brain capacity. Seasonal growth rings in their bones revealed that these creatures experienced rapid growth in their early years, reaching 70% of their adult size within just 4 years. This accelerated development, combined with evidence of sophisticated parental care, suggested a species that invested heavily in the survival of each individual, a strategy more commonly associated with mammals than dinosaurs. Combat injuries preserved in multiple specimens pointed to intense competition between individuals, particularly during mating seasons. These injuries, along with display features like their proto-feathers and enlarged visual cortexes, suggested complex social behaviors including ritualized combat and possibly even courtship displays. The presence of these behaviors in a late Cretaceous theropod challenges our understanding of dinosaur social evolution. The predatory adaptations of Enigmatherium represented the culmination of over 150 million years of theropod evolution. Their hunting strategies combined the raw power of traditional large theropods with unprecedented levels of precision and coordination. How would these creatures have continued to evolve had the asteroid impact not brought the age of dinosaurs to an abrupt end? What level of sophistication might their descendants have achieved given another few million years of evolution? Environmental evidence suggested these creatures were adapting to increasingly unstable climate conditions in the late Cretaceous. Their flexible hunting strategies and social cooperation might have been responses to these challenges, representing evolutionary innovations that could have ensured their survival through the tumultuous end of the Cretaceous period, had fate not intervened in the form of a massive asteroid impact. The discovery of Enigmatherium gobiensis has fundamentally altered our understanding of dinosaur evolution and the complexity of prehistoric ecosystems. As research continues, each new finding forces us to reconsider long-held assumptions about the capabilities and behaviors of ancient predators. The implications extend far beyond paleontology, touching on fundamental questions about evolutionary processes, cognitive development, and the potential for intelligent life to emerge under different evolutionary pressures. One of the most profound impacts of the Enigmatherium discovery has been its influence on theories of convergent evolution. The creature's advanced features, from its sophisticated forelimbs to its enlarged brain capacity, mirror adaptations seen in much later mammalian predators, suggesting certain evolutionary solutions may be more inevitable than previously thought. This parallel development, separated by 66 million years, raises intriguing questions about the predictability of evolutionary outcomes under similar selective pressures. The revelation of their social complexity has sparked intense debate about the nature of intelligence and its evolution. The evidence of coordinated hunting, extended parental care, and possibly even primitive tool use suggests that the path toward higher cognitive function may have been embarked upon multiple times in Earth's history, only to be cut short by extinction events. This realization has profound implications for our understanding of how intelligence evolves and the potential for its development in other species, both on Earth and possibly elsewhere in the universe. The technical advances developed to study Enigmatherium have revolutionized paleontological research methods. New imaging techniques, molecular analysis protocols, and biomechanical modeling approaches created specifically for this investigation are now being applied to other fossil specimens, leading to fresh insights about previously well-studied species. These methodological advances represent perhaps the most lasting legacy of the Enigmatherium discovery, providing tools that will continue to unveil prehistoric mysteries for generations to come. Questions about their extinction become particularly poignant when considering their advanced adaptations. These creatures had evolved solutions to many of the challenges that traditionally limited large predators. They had overcome the constraints of their size through enhanced agility, developed sophisticated social strategies to improve hunting success, and achieved unprecedented levels of behavioral flexibility. Yet all these advantages proved insufficient against the global catastrophe of the asteroid impact. What insights might this offer about the vulnerability of even the most successful species to rapid environmental change? The discovery has also forced a reevaluation of the Cretaceous-Paleogene extinction event itself. The presence of such advanced predators at the very end of the Cretaceous period suggests that dinosaur evolution was far from stagnant when the asteroid struck. Instead of a group that had reached its evolutionary limits, as some had previously suggested, the dinosaurs appear to have been continuing to innovate and adapt right up until their extinction. This realization adds a new layer of tragedy to their demise. What evolutionary marvels might have emerged had they been given more time? Perhaps most significantly, the Enigmatherium discovery serves as a humbling reminder of how much we still have to learn about Earth's prehistoric past. If such remarkable creatures could remain unknown for so long, what other extraordinary species might still lie undiscovered? How many other evolutionary experiments, failed or successful, remain hidden in the rock layers beneath our feet? Every new discovery has the potential to revolutionize our understanding of life's history on Earth. As research continues, the mystery of Enigmatherium gobiensis keeps unfolding. Each answered question seems to spawn several new ones. How widespread were these creatures across the ancient world? Did they interact with other advanced theropods like Tyrannosaurus rex? What role did they play in shaping the evolution of their prey species? The answers to these questions may lie waiting in unexplored rock formations, promising future discoveries that could be equally revolutionary. The legacy of Enigmatherium extends beyond its scientific importance, capturing the public imagination and rekindling interest in paleontology among a new generation. It reminds us that the history of life on Earth is far more complex and surprising than we often imagine, and that some of the most important discoveries may still lie ahead. What other extraordinary creatures might be waiting to be discovered? What other paradigm-shifting revelations might emerge from the fossil record? The story of Enigmatherium gobiensis is not just about the past. It's about the endless possibilities that await future exploration and discovery. As we stand in the 21st century, looking back across 66 million years to the world of Enigmatherium, we are reminded that our understanding of life's history is still evolving. Each new discovery has the potential to reshape our perspective on the past, and in doing so, alter our vision of what might be possible in the future. The mystery of the forgotten predator of the Gobi Desert may have been partially solved, but its full implications are still unfolding, promising to influence scientific thought and research for generations to come.